Okay, welcome back. So I'm working with a new tablet. You'll have to let me know if you notice any writing differences. I suspect things will look a little bit different than they did before. We're moving on to section 11.4. This is called Separable, Bernoulli, and Nonlinear Homogeneous ODEs. I use the extra quantifier nonlinear in front of homogeneous here because they're not the same homogeneous ODEs that you encountered in the linear section. The word homogeneous isn't related at all, and yet the etymology kind of makes sense for homogeneous in both directions. So, so we kind of have to work with that. We're stuck with like this idea of nonlinear homogeneous not being anywhere close to linear homogeneous. They're just like two different things, and we both use the word homogeneous. But these are kind of the three situations in which an integrating factor is somewhat easy to find. There's like a very natural integrating factor to these sorts of nonlinear ODEs in one dimension. And so we're going to start with separable because it turns out that Bernoulli and nonlinear homogeneous reduce to a version of separable if you make an adequate change of variables. So we're going to start with something called a separable ODE. And this is going to be a nonlinear ODE in one dimension, first order, where my g on the right-hand side, if I have y prime equals g of x and y, the g on the right-hand side can be written as a ratio of phi of x and psi of y. So these are two separate functions. Let me make that a little clearer here. So I have a function only of x divided by a function only of y. And in fact, stating it in that way feels awkward because I present my first example and I write y prime is x times y squared. And that's why stating it in the above way is awkward because I was saying it's divided by, and here you'll notice that it's actually multiplication of two functions, one of x and one of only y. But it's obviously you can always write a division as a multiplication by a reciprocal. And so you can reduce this to the case of a phi of x divided by a psi of y. You can write any multiplication. This will always be phi of x times psi of y inverted, right? And so it's really a multiplication of a function of x and a function of y is equivalent to a division of a function of x and a function of y. So all of those cases are considered separable. The only reason I present it to you in this situation, most textbooks will present it in an alternative situation, is because actually our theorem, which gives us the solution to these, is much easier to state in the setting where we write it all as a division. Because if I write the right-hand side as a division of phi divided by psi, then actually the implicit solution is just given by capital psi of y equals capital psi phi of x plus c, where the capitals are antiderivatives. Okay, so what we want to think about here is that this is the antiderivative of lowercase psi, and this is the antiderivative of lowercase phi. So all I do is I take their if I identify a phi and a psi, which one is divided by the others, then I compute their antiderivatives. I set them equal to each other, and because it's an antiderivative, they can possibly differ by a plus c. And then that's my implicit solution because it's not quite solved for y right there. An explicit solution, if I have the ability to invert psi, capital psi. If you can invert capital psi, then you have an explicit solution. It's given by capital phi, so the antiderivative of phi on x plus c, and then you take the antiderivative of psi and you compute the inverse function of that, and then you get an explicit solution. This looks a little bit strange, right? The notation here maybe looks strange, but we'll look at this above example. Relook at the example right here. This example will compute the solution to that ODE right here. So after the proof relies on the previous section, so it should look fairly standard if you recall the previous section. But we're on the same example, and if we rewrite this as x divided by y to the negative 2, that's me identifying both phi as x and psi as y to the negative 2. I can compute antiderivatives of both of those. The antiderivative of x is x squared over 2. The antiderivative of y to the negative 2 is negative, just to verify this for all of you, the antiderivative of y to the negative 2 is y to the negative 1, and you divide by its power, so you get negative y to the negative 1. That's what capital psi should be. And so we have capital psi equals capital phi plus c is our implicit solution. And then if we want to reduce that to an explicit solution, this is a very, very easy function to invert, right? I'm just going to take the negative of both sides. Technically, I'm absorbing a negative sign into my constant, but I'm going to take the negative of both sides and then the reciprocal of both sides, and I recover my solution. So this is the solution to the nonlinear ODE, which is given by that. Okay, so after having taken care of separable, we can now talk about these special cases of Bernoulli and nonlinear homogeneous, which in many ways just reduce to the separable situations. So we're going to call a Bernoulli ODE an ODE of the following form. It almost, I'm saying g of xy, so the right hand side of my ODE looks like that looks linear. It's linear. And this looks almost linear. Right, I put a question mark there because there's this p, so there's this p power. So a Bernoulli type is like a sum. This is like a sum of first order linear in 1D, right? With almost first order linear in 1D. Because if p were 0 or p were 1, if that were a power 1, then we would truly have something linear homogeneous, and the power p were 0, we'd have something linear non-homogeneous in one dimension. And so this is similar to those, but not quite. But that's what makes us think that maybe we could get under a change of variables to something that is actually solvable. So looking at an example of one of these, I can see that the right hand side here is a multiplication of a function of x times y. So there's like my linear part. And then a function of x times y to a non-zero or non-1 power. And that's what gives me Bernoulli type. So this first term is like, okay, that's a linear, but then if I add this special term, that's Bernoulli type. And so technically the type above here is also of Bernoulli type, because you can say like the linear term was 0, and then the Bernoulli term, which you add, which is just the power of y, is y squared here. So p would be 2, but in this bottom setting, I guess m is 1 over x, f is x squared, and p is 3. So there you go at the bottom. The next proposition talks about the solution to these types of ODEs. And they look a little bit ugly, right? So we're just going to start by stating the ODE that we're going to try to solve, and then here's our solution. But you should start to recognize that this solution actually looks a lot like the first order linear ODE, non-homogeneous, right? So with the non-homogeneous, if I got rid of this, if I got rid of this, and if I got rid of this, then this is first order linear ODE in one dimension. So that's the first order linear ODE in one dimension. It makes a lot of sense because as p approaches, I guess 0, this is what you would recover, right? And the limit as p goes to 0, that's what you'd recover. And of course, the limit as p goes to 0 there, it becomes first order linear ODE. But we have to play this game where you have some non-zero p's sitting around. And the way that we prove, right? So the way that you prove that this is the solution is actually by using separability under a change of variables of letting y be zx e to the mx, where m is this integrating factor, or really the term that you also saw in your linear ODEs section. It's also the integrating factor if you go through some integrating factor techniques. Then you can just solve this equation using separable methods, or even linear ODE methods, because in one dimension they can sometimes reduce to each other, and then you get your solution. In fact, something that the next remark touches on is, it's not quite clear, but even as p goes to 1 and that turns into 0, that turns into 0, and that turns into infinity, you do also technically recover the linear solution to this ODE. So that's kind of a fun thing to think about. Okay, so now we can solve the ODE using our proposition, because we've identified this as a Bernoulli type ODE where m is 1 over x, f is x squared, and p is 3. So let's just jump up to our solution right here, and I'm going to do this by hand for all of you so you don't have to get forced to read everything through. We're going to take e to the integral of 1 over s ds, and then we're going to multiply by 1 minus p. P was 3, so the 1 over s, this was m, p was 3. And then we're going to integrate e to the 3 minus 1, so that was p again. And then integral 1 over s ds. F of s we decided was s squared. So that's f. And then ds plus c. And I have 1 divided by 1 minus 3, because 3 was p. So let's start to compute this. That's e to the log x. Each of these integrals are integrated up to x, right? Okay, so that's e to the log x, negative 2 integral e to the 2 log s squared ds plus c, all to the negative 1/2 power. So I guess that gives me x and then I have -2 integral. This term is going to give me s squared, so I have s to the fourth here, ds plus c, that's an integral in x, -1/2. If I compute that through one more time, I have x, and then this integral will be s to the fifth over 5, right? X to the fifth over 5. So 2/5 x to the fifth plus c minus 1/2. If I decide to make that a little bit prettier, that's x divided by square root c minus 2/5 x to the fifth. So that is my solution to this Bernoulli type ODE. Let's scroll down and make sure that I did that all correct, because sometimes I can screw up my integration. Looks good so far. Yep, that is exactly what I had right in the middle of the screen right here. Okay, so very good. Then we're going to move on to one more type, and this is going to be the nonlinear homogeneous type. And these types are going to have a slightly different form. These types have a right-hand side of my ODE, that's being G there. So the right-hand side of the ODE looks like a single function, f, of the ratio of variables y divided by x. Okay, so if I can find a single function, that was supposed to be the word single, not since. If I can find a single function, f, which once you plug the ratio of variables y over x into f, then you recover the right-hand side, I'm going to call that nonlinear homogeneous. So I'm looking for one function that has a bunch of ratios in it. So the following ODE is not written. It doesn't look like f of y over x, but I'm claiming that it is f of y over x because I can simplify this a little bit, right? If I spread the denominator out to each part, I get something like y squared over x squared plus xy over x squared minus x squared over x squared. And if I go through one more step of simplifying that, that simplifies to y over x squared plus one of these x's cancels. So then I have something like y over x plus 1. And in this form, it's very clear that for something like f of s being like s squared plus s plus 1, if I just plugged y over x in for s, right, putting y over x in for both of my s's gives me, it's a single function that has y over x. It's like a ratio inside of each of its terms, right? There's that ratio there, that ratio there. And so this is a nonlinear homogeneous type because of what I just said. And now we have a proposition which tells us how to solve this, and the proposition is not so great. It's a little bit ugly of a solution. So given the nonlinear homogeneous ODEs, so supposing we already identified the f, for which if I just plug the ratio y over x into the function f, I get the right hand side of the ODE, I have a little bit ugly of a solution here. So I have to integrate 1 divided by f of s minus s, and I'm integrating that function from y naught over x naught up to y over x. So here you can see those ratios kind of come into play, that y over x ratio becomes important. And then on the right-hand side, I just get log x plus c. And this is starting to look like, it's starting to look like maybe we're using separability here, because this is like, think about it like capital psi. Since capital psi was an antiderivative of y, think about that as like capital phi plus c, since that was also an antiderivative. So it's like that's an antiderivative of 1 over x. And there's like the plus c is sitting around. And this is what I mean by like it gets converted to a separable ODE. And so you'll see that in the proof here where we make a change of variables, y of x equals z of x times x. And then upon doing that, you go through the steps of separability in the z variable to recover your solution. Now what we can do with that is we can in fact solve this ODE, because I'll use this at the bottom to solve this ODE. So let's recall that this was actually y over x squared plus y over x minus 1. And so f of s was s squared plus s minus 1. And so if I'm going to be computing this, all I have to do is integrate. I'm going to leave those bounds off because they're so tiny. 1 divided by this minus s. Okay, so if I subtract s from there, I get s squared minus 1 ds equals log x plus c. And there are a few ways you can actually integrate the left-hand side here. You can either do some trig sub on it, or you can You can do partial fractions on it. I like the partial fractions version of it better. No matter what way you go about integrating the left-hand side, you're going to get log of 1 minus s divided by 1 plus s. And of course, we evaluate this at the bounds, y0 over x0, y over x equals log x plus c. Now, notably, if I integrate, or if I exponentiate both sides there, what I'm going to end up with is actually 1 minus s over 1 plus s evaluated at my bounds equals cx. And plugging in y over x to the left-hand side, I'll end up with 1 minus y over x over 1 plus y over x, and then the initial conditions, 1 plus y naught x naught equals cx. So this is actually my implicit solution to the nonlinear homogeneous ODE, and ideally I could solve that solution for y all by itself. Now, if I scroll down, you'll see that I can actually do that. It doesn't exactly seem like it's something you should be able to solve for y, but you go through, a fair bit of work, and when you do go through all of that work, you get 1 minus cx squared, 1 plus cx squared. Oh, I guess I forgot a 1/2 sitting around when I integrated. Yeah, there should be a 1/2 there, which is where the x squared is coming from. But you can actually solve that for y. It's a little bit crazy. You wouldn't believe that you could solve it for y, but it's a little bit crazy. You go through the work and you can solve it for y, and you see your one free parameter of c sitting around. You'll notice that I got rid of the initial value, the initial condition. That's because when we don't actually have an initial condition, I just let y0 over x0 equal 1. And if you let y0 over x0 equal 1, then the term that we ended up with disappears. That became 0. So that's why I didn't have that little y0 over x0 in the solution at the end there. But yeah, that's the solution to that then. And those are the 3 types that we have easy integrating factors for. And that's the end of this chapter. So I'll see you in class. Bye.